Hi everyone, today we're going to talk about section 9-2, exponential functions. The table and graph below show an insect population that has increased over time. The initial or the starting amount of the insect population was just 2 insects. However, after 1 day it increased to 6, after 2 days it increased to 18, and after 3 days it increased to 54 in the population. If you look at the graph of these points, you can kind of see that if you connect them, they're not going to make a straight line. They're actually making a curve, and the curve is increasing pretty quickly. This is an example of an exponential function. An exponential function is written in the form f of x. Remember, this is function notation. It's just another way of writing y equals, but it really literally stands for the function of x is equal to a times b to the x power. When you're evaluating exponential functions, it's important to remember your order of operations. Since it's a times b raised to the x power, you're going to do the b to the x power first. We do our exponents first, and then multiply that by a. A is actually the starting value or the initial value of the population or of whatever is growing exponentially or decreasing exponentially. And in order for these to actually always be exponential, a cannot equal 0, because if a was 0, then no matter what your x value was, the answer would always be equal to 0. And b cannot equal 1, because 1 raised to any power is always 1, and that means it would not grow exponentially as well. B also has to be greater than 0 for it to grow or decrease at a exponential rate. It can't be a negative number. So let's look at a couple of examples. The function f of x equals 2 times 3 to the x power models an insect population after x days. What will the population be on the 5th day? The thing about exponential functions is that the variable is actually the exponent. So in all the other types of functions we've done, linear, quadratic, the exponents were not variables. Here, the exponent is actually the variable in the equation. In order to evaluate, though, you're just going to plug in 5 for x. So f of 5 would just be equal to 2 times 3 to the 5th power. Remember, order of operations, you're going to do 3 to the 5th power first and then multiply by 2. If you have a scientific or a graphing calculator, if you type it in exactly how it is written here, your calculator does know the order of operations and will do it correctly for you. 2 times 3 to the 5th power is equal to 486. So that means the population, and this was this example, the population after just 5 days would be 486. So the population of bugs is growing very quickly. The function f of x equals 1500 times 0.995 to the x power, where x is time in years, models a prairie dog population. How many prairie dogs will there be in 8 years? So if you look here, this number is actually less than 1, which means this is still an exponential function. However, it's decreasing. So instead of the population getting bigger, since you're multiplying it by a number less than 1, you should be getting a smaller number. If you work out a function where your b value is in between 0 and 1, and you get a number bigger than the initial amount, then there's a mistake. So always just pay attention. If your b value is greater than 1, like it is here, that means your answer should be more than your starting amount as long as your x is a positive number. And if your b value is less than 1, like it is here, your answer should be less than your starting amount as long, again, as if x is positive. So the question is, how many prairie dogs will there be in 8 years? So that means we're finding f of 8. So what we're just going to do is change x be equal to 8. So we're doing 1500 times 0.0995 to the 8th power. Again, you do the exponent part first and then multiply by 1500. We are talking about prairie dogs, which is an animal, so we're going to just round to the nearest whole number. So after 8 years, there'd be approximately 1,441 prairie dogs. Hopefully you remember that linear functions have a constant first difference and that quadratic functions have a constant second difference. Exponential functions do not have any constant differences. They do, however, have a constant ratio, which, just like we talked about in geometric sequences, means that you're multiplying by the same number each time. As your x values increase by a constant amount, the y values will be multiplied by a constant amount. The amount is represented by b in the formula. So b is basically the common ratio, or what you're multiplying by each time to get the next number. So if you're given a function or a relation, a set of ordered pairs, and asked if it's an exponential function or not, the best way to look at it is to put it in table form. And again, you do want to make sure that your x's are increasing by a constant number. Here, they're increasing by 1. And then you're not worrying about how much it's increasing by for the y values. You're worrying about if there's this constant ratio. So is there a number that you can multiply each x value by to get to the next x value? And if you look here, 1.5 times 2 is 3, 3 times 2 is 6, and 6 times 2 is 12. So the answer is yes, this is an exponential function. Our second example, when we put it in table form, our x's are increasing by 2 each time. And when we look at our y values, to get negative 9 to turn into positive 9, you're multiplying by negative 1. However, to get 9 to equal 27, you're multiplying by positive 3. And to get 27 to be 45, you're multiplying by 3 halves. Because we do not have common ratios, we're multiplying by a different number each time here. This is not an exponential function. To graph an exponential function, which you have learned about and kind of done activities with matching so far, you need to choose at least 4 values of x. You should have a positive number, a negative number, and 0 included in those 4 values. And then you're just going to plug them into your function rule, solve for y, and then plot your points and connect it with a smooth curve. One example is y equals 3 times 4 to the x power. I chose negative 1, 0, 1, and negative 2 as my x values, and then you literally are just going to plug them in. So 3 times 4 to the negative 1 would be 3 times 1/4, which is equal to 3/4. And then 3 times 4 to the 0 power would be 3 times 1, which is 3. Remember, any number to the 0 power is equal to 1. 3 times 4 to the first power would be 12. And then 3 times 4 to the negative 2 power, 4 to the negative 2 power is actually 1/16, and then 3 times 1/16 is 3/16. When you plot these points, you're going to do the best that you can. This point here is negative 2 3/16. This one right next to it is negative 1 3/4. 0, 3 is our initial value. That's our y-intercept. And 1, 12 is the point all the way up here. Exponential functions do continue forever in both directions, so you put arrows on both ends. It's important to realize, though, that they will never actually cross the x-axis because there's no number that you can plug in to this function in order to make it equal to 0 or to a negative number. No matter what you plug in here, you're always going to have a positive number. So the graph of an exponential function never actually crosses the x-axis. It just gets infinitely smaller and smaller and smaller, but never actually equal to 0. Let's just look at one more example. The function here is y equals negative 5 times 2 to the x power. Again, I chose negative 2, negative 1, 0, and 1. When you plug in negative 2, you end up with negative 5 over 4. When you plug in negative 1, you get negative 5 halves. When you plug in 0, you get negative 5. And when you plug in 1, you get negative 10. When I graph this exponential function, it's actually on the other side of the x-axis. It goes through quadrants 3 and 4 instead of quadrants 1 and 2. And that's because my a value is negative. When you plot these points, this point right here is negative 2, negative 5/4. This is negative 1, 5, negative 5 halves. This is 0, negative 5, which would be the starting amount. And this is 1, negative 10. Again, it continues in both directions forever, so arrows on both ends, but it never will actually cross this x-axis and become positive. So it's never going to be equal to 0, and it's never going to be a positive number. Okay. That's all that's in 9-2, so you're going to complete some quick checks on a Google form right now. If you have any questions, just let me know.